Okay, so welcome to our topic on chromatography. So we'll get started right away. And pretty much what chromatography is that it's a separation of compounds based on their affinity for the mobile and stationary phases. So the basic principles are that the mobile phase, so mobile or moving, and stationary or not moving. Okay, different compounds will have different affinities for the mobile phase. So they'll those that have a stronger affinity for the mobile phase, they will be moving faster, okay, compared to those who have a stronger affinity for the stationary phase. Or in other words, they won't be moving, or they won't be moving as much. So if you can imagine this sort of column, and it looks like something like this, I guess. And there is the mobile phase. So let's say the mobile phase is here in blue. Okay. So the mobile phase is going down. Okay. And if our sample is in red, what our sample will do is it will adsorb onto the stationary phase. So the particles in black basically will adsorb onto those. So it'll basically attach onto those, right? And here it won't move. It will be in the stationary phase. But then it can also desorb back into the mobile phase and can continue to move down this column. And eventually it'll come out through here. So it will elute. Okay. And that's when we know that it's come out of the column. So depending on the affinity of the compound for the mobile phase and its affinity for the stationary phase, it might elute faster or slower than other compounds. And as you can see here, if a molecule if a molecule moves faster through the column, okay, that means that it has a greater affinity for the mobile phase, and the mobile phase is a solvent. Okay, so let's move on. Now, remember that it's the strength of the intermolecular forces that dictates how strongly a molecule is going to adsorb onto the stationary phase. So if it has strong intermolecular forces, namely dispersion forces, that it can form with the stationary phase. So the stationary phase might be like a few nanoparticles. It's basically like a solid, something solid that a particle can adsorb onto, can attach onto basically. So if it's got a really strong affinity for that stationary phase, because of its strong intermolecular forces, then it's going to spend a longer time attached to that stationary phase, and therefore it's going to move through the mobile phase more slowly. And I think hopefully that makes sense, because if you're staying attached to the stationary phase for so long, you won't be able to move through that mobile phase or move through the column. You won't be able to move down the column as fast. And so if that's happening, essentially what it's got, so if you're spending so much time in that stationary phase, you won't be able to move through as fast. And you won't be able to move through the column as fast, basically. Now, let's say, however, on the other hand, that a compound can dissolve more easily, or it has a strong affinity for the mobile phase. Well, in that case, it's going to be easily able to just move down the column because it's going to be strongly attracted towards this mobile phase. And so it'll just continuously move through the solvent, and it will spend more time dissolved in the mobile phase. So more time dissolved in the mobile phase means that it's a part of the solvent. So the solvent's in blue, and it'll just keep moving along with the solvents down the column. So hopefully this sort of general idea is making sense. Okay, so what we're going to do now is we're just going to take a look at a particular type of chromatography. And this type of chromatography is called thin layer chromatography. Now, what it does is that, so we can actually use paper in this, actually, for example, is we have like a starting line over here. So, or we can also call this like an origin. So, or it can also be called like the origin point. Okay. And what it can do is it will separate small amounts of the substance that are dissolved in a solvent. So let's say we have some sort of a solution and we've got different substances dissolved in it. And we can run this sample through thin layer chromatography. And these different components, so one here, one here, one here, they'll separate from each other depending on how attracted they are to the mobile phase. So that would be the solvent versus the stationary phase. Now, what we can actually use this more for qualitative analysis. So qualitative analysis, what that means is basically determining the identity of a molecule. So for example, we might have some unknown sample, and we might be like, okay, so we know that these samples, so this one, this one, this one, and these are all in the solution. We might want to test, well, is this particular solution, does this particular solution contain some particular compound? So let's say we got this, we got a blue, this, let's say we had another sample, we ran it through, and it stopped over here. So that's this distance is how far from the origin that particular solute traveled. And so if that's the case, what we can do is we can see, well, okay, they have a similar RF, and RF is basically it's a measure of how far the solute has traveled from the origin compared to how far the solvent has traveled. And so if this RF value is similar for both of these, what that suggests to us is under the same conditions, and the conditions have to be the same, under the same conditions, if we get the same RF, that these two molecules, they must be the same. So it helps us to basically determine the identity using chemicals that we know of. So we know that we might know what this blue chemical is. So maybe let's whatever compound it is, then that can help us to determine the identity of this compound over here, which we might not know. So hopefully that sort of makes sense about how this is useful. But the general idea is, again, that we have different solutes, okay? And these solutes will be attracted to the mobile phase, and they might and they might be more attracted to the stationary phase. So they'll be attracted to both of those phases to some extent, and they'll adsorb onto the stationary phase and desorb onto the mobile phase. And depending on which one they have a greater affinity for, they'll spend more time in that phase. And by spending more time in that phase, that will dictate what their RF ultimately is. And we can use that to determine the identity of a compound. We can't really use it to determine the concentration or like how concentrated that compound is in a solution. We can only really use it for qualitative analysis, as I've said. So let's move on. Now, again, this is pretty much like this is the same concept, okay? But I really just want to drive home the factor of the RF. So RF just stands for retardation factor. And again, it's for determining the identity of a chemical. And as I said before, a few drawbacks of this include that you can't use it for quantitative analysis. And so what quantitative analysis, what that might tell us is what is the concentration of this solution, or what is the concentration of this particular compound in that particular solution. So that's a drawback that you should be aware of. And just know that thin layer chromatography, it is quite limited. So you can't do as much with it as with other types of chromatography. Okay, so what I'd like to do now is to determine the identity of X. So like this is a question that I'd like you to attempt. So before we go through it together, I'd like you to sort of just pause the video and then try and attempt it yourself.